Today we're going to look at VisIt, and we're going to change things a little bit from yesterday because of the nature of VisIt. We will not have to mess up with this complicated tunnel thing and SSH multiple connections, because VisIt has it all embedded into one click. That's one advantage of it. The other thing that will change is that I have prepared one big exercise, and we've tested this already I personally tested this exercise at the Supercomputing Conference tutorial last November in Denver, and it worked out quite well. So I'm hoping we have the same success here. So this is a fluid flow showcase exercise, probably more than 30 minutes. We'll see how much we get along. The data has been prepared for you. It's here at CSCS under the course directory. This is what we'll intend to do. And then the rest should actually be shorter. This is why I feel we can steal some time from the second part of the morning to accomplish what we did. So let's get started anyway, to not waste any more time. VisIt is available at CSCS on Eiger, Pilatus, yes, Castor. As of yesterday night on Rowthorn. Rowthorn is a machine at CSCS that may be interesting for you because it has 2 terabytes of RAM. It's the only such machine with a large memory available. VisIt is also available on Rosa and on Daint. Well, Daint is not open to the public yet, but Rosa is available. Some of you must be users of Rosa. I've done actually a full-length movie of fluid dynamics this last summer on Rosa, so I can tell you it works really well. How do you do it? You develop your Python script using the graphics cluster, and when you have a Python script, you run it on the supercomputer. That's really the way you should use it. And it's keep in mind that it's much cheaper to run on the supercomputer than on the Eiger node, because it's also much more efficient. Presumably, you run your simulations on Rosa, so your data are dumped onto the scratch file of Rosa. If you do the visualization on the same machine, there's no data copying anywhere. It's all one-stop shop. If we run VNC at CSCS, we'll have to use this particular option minus hardware-accel on Eiger. But let's try maybe to, oh, actually, those of you who have not installed VisIt yet, you'll have to go through this. So this is the opening page of the tutorial in Denver, which we did. The full-length tutorial, just like yesterday, is found on the wiki at this particular address. So visitusers.org. That's the point of reference where you'll find everything else. And this is a reduced version of the tutorial of November. So there is basically fundamental concepts which are explained. And I think I can go a little bit faster here because we've learned some of this yesterday. Then there will be a guided tour by myself, and you should follow along what I do. And then this exercise, which is the blood flow inside an artery with an aneurysm. And so we have flow here going up like this, and then into this aneurysm. There's a lot of vertical structures here, and then the flow finally comes out. And we're going to do several exercises with this data set. This is a time-dependent data set. Some of the exercise will be with the first time step, just to get some practice, and then eventually for the more advanced users, you'll be able to do the full particle animation. Here are the 4 persons who are responsible for the tutorial. So Cyrus, Hank, Brad, and myself. There. Terminology in VisIt, we talk about zones and nodes. Zones are the same thing when I say cells or elements, finite elements, they're the same thing. Well, VisIt calls them zones, so this is to know. And then fields are called, well, scalars and vectors, and so forth. There's nothing new here. Pseudo-coloring will be the first tool we will learn, and pseudo-coloring is just like we used to color geographic information like this with colors. We do the same in 3D. This is scalar to color mapping, but we call this pseudo-color in VisIt. Contouring, going from 2D to 3D, there should be no secret here for you. You know what an isocontour is. Volume rendering is a little bit different. We have not seen it yesterday. I will show you an animation I have made here with VisIt, which uses volume rendering. It will be a lot more interesting than seeing a static image like this. In fact, why don't I show you this video immediately as a motivating instrument. Of course, I have to find it. There we go. This one, or this one, or this one, this one. Echo. So here's another example of a video which was made on ROSA, on the supercomputer. So this is a data simulation from some colleagues at ETH Zurich. We're looking at the flow through this piston going into the combustion chamber here. And this what we see here is this volume rendering. So volume rendering is a display of there's no polygonal surface, no polygonal elements, but we do a simulation of the integration of the light traversing a semi-opaque object. So this video is actually, you see, a time-dependent problem. And to make it all synchronized, there's quite a lot of work. So a lot of Python programming to be able to reuse and to restart the simulation at the right place, etc. There. So I think we've had a very quick look at volume rendering with this particular example. Volume rendering, just to finish, is a very expensive technique to compute. I cannot pretend to make a volume rendering on my screen and then move around with the mouse, and it's not interactive at all. So if you want to do something like this, please talk to me. There's a lot of optimizations that need to be put in place to make it a useful and effective experience. Particle advection, really the foundation of flow visualization. The problem is this, moving a particle through a vector field. And this is what we will do in our exercise. Already this morning somebody was asking me about streamline. It was you, yeah. So we're going to do streamlines this morning with the exercise. Here we have a very crude display of a vector field. I hardly ever do this type of display anymore because it's not very pretty. We have a vector field, so little arrows, but they're all bunched up like this, or here we have some empty space. It's not very effective. There is a technique called line integral convolution, which I was planning to show you yesterday. It's available only in ParaView, however, but it's in your notes. In the notes Oh, did I put that at the very end? There's a link that I have put. If you go to the wiki, you can find representations of this technique, which uses a texture of noise which is advected, which is convolved with the velocity field to show a really nice display of velocity. This would be something you could use also as an alternate to this type of display. Line integral convolution. Yes. Meshes, so no secrets now. We all know. One thing we didn't mention yesterday is that besides this standard type of meshes, we can have also molecular type data. Okay, so this is a full first-class citizen in VisIt. We can have, I can load data in PDB format, in Gaussian format, in GROMACS, etc. All those standard outputs of simulations. There will be the difference between data that is stored at the cell centers and data that is stored at the node center. And that's about it. This distinction between storing data at the center of the cells or on the vertices. However, just yesterday evening, there was a commit of a new code into the SVN repository of VisIt to do streamline where data are placed at the midpoint of edges and at the midpoint of faces on 3D cells. So this could be very interesting. I know several people have asked me for that in the past. So data that is not in this conventional structure but stored right here at the midpoint of the edges or at the midpoint of the faces.
Are the meshes always before connection, or do you also have
hexagonal? Yes, we have hexagonal. Yes, we have them. They are first-class citizens, okay, in the VTK data structures. There exist. In fact, yeah, I helped put that into place several years ago. The VTK prism, the VTK, what is it called? Hexagonal prism and pentagon-based prism, which means that the pentagon exists as a cell, the hexagon exists as a cell, etc. There is a case where some people use spectral codes, and this is similar. In spectral codes, the data for rendering purposes is actually triangularized or tetrahedralized, and we see actually additional lines connecting those vertices together. And it would be the same case with the hexagons, that for rendering purposes, we would see the additional triangles, but internally they are used as hexagons and etc. I think that's all I need to say for now. Interesting, we didn't see that yesterday. We can also have the case where we have materials. Okay, this is often found in chemistry, for example, where we have volume fractions, area fractions. So this is the case where we have different volumes, different materials which don't occupy the full 100% of a cell. So this can be done perfectly well with VisIt. Example, yeah, in chemistry where a particular material like the air is composed of many gases, so N2O2, argon, CO2, etc. You can have all those different species as percentages of the full cell value. So the abstractions are the following in VisIt: the databases, the plots, the operators, the expressions. Expression, there's a very simple case. Somebody asked me this morning before we started. I read my data, I have velocity data in my file, but VisIt doesn't see the velocity field. Why not? In the particular case, my guess is that VisIt reads the 3 components of velocity as individual scalars, and that's it. And this is where we use expression, which is a way to derive additional expressions, yeah, so to speak. And this is very, very trivial to say velocity is actually a composition of the u, v, and w parameters. So this is not a problem. Queries, we saw some queries yesterday. Today we're going to see more queries, and we're going to do this in the exercise, so you'll have to follow carefully. Pipelines, this is my favorite topic. So here's how pipelines are organized in VisIt. We're going to see several scenarios. The first one will be to open a database and do a plot. Okay, the plot is the name inside VisIt which you need to do, and the plot is how you render your data, and then you can modify the way you render your data by adding an operator. So the operator will transform your data. For example, plotting a grid of data will show you the bounding box of your data. If you modify it with an isocontour operator, you will see the isocontour. So this will be really if you follow me carefully, it's a little bit different than ParaView, where I build the pipeline from the top to the bottom and I keep adding things. Here, I do a database, here, a plot, and when I put an operator, the operator is inserted in between. And here you can insert multiple operators, but the plot is always at the bottom of the pipeline. Okay? Of course, you can put your expression here before the plot, etc. Here's an example. Calculate the magnitude of the velocity. This would be typed exactly like this, so it's very close to your standard mathematical notation. There's a full, long database, pipeline, I want to say, a database, an expression, an operator, a plot, and a query. When we query data, there will be the option to query the original data, meaning the data at the very top of the pipeline, or to query data at an intermediate step of the pipeline. So we'll have to be careful in the graphical user interface to say plot the actual data or plot the original data. So this is where I have to work here. Database, plots, operators, expressions, queries. All of those you see at those following addresses on the wiki, and I'm going to start very simple with a demonstration. The advantage of VisIt when you install it on your computer, it installs a small set of data files which are used for the wiki and for the tutorial. So it's all embedded in a single installation package. And they are found in a subdirectory called data. So if I open my file like this, and I have to find where I put it, which is something interesting. This is a challenge. Oh, there we go. So app data VisIt 201 data. There we go. All the examples that are provided with the installation of VisIt are in the silo data format. And the first one we usually use for tutorials is called noise.silo. So I will open this file. Wonderful. Maybe the path is invalid here. Try to use the following format. This is unexpected. I'm not sure this path is actually correct. Open file. Wait, I have to see. So here's what the reason is I've never read data on my laptop. I always read data on the remote server. So I'm going to go directly to the remote server, and that will take care of it. Launch, advanced, minus reservation equals course. Okay. I have some data loaded. And the first questions beginners ask is, I loaded my data and there's nothing on the screen. That's the first barrier. How do we verify that the data has been loaded? Here there's a menu called File Information, and it shows that I have loaded a data set here, which is stored on the Eiger file system. It's of file format silo. It has one time step. It has one mesh called mesh. It has another mesh, which is a two-dimensional mesh called mesh 2D. It has a point mesh. It has scale fields. One of them is the air volume fraction. The other one is the chrome volume fraction, etc., etc. So it's there. And by the way, in addition to the variables that are stored in the file, I already have some expressions which are predefined. Here, for example, I have the tensor components. So a tensor, this is the 3x3 matrix of the gradient of the velocity vector. And those are automatically defined for me by the VisIt software. I have a couple of fields, of vector fields. One of them is the air volume fraction gradient, and one is the gradient. So why do I not have any pictures on the screen? It's because I didn't add any plot. So this is the beginning of building a visualization pipeline. I will add a pseudo-color plot of my variable Hardy Global, for example. And I have to click the draw button to see anything. There. Now I will delete this plot and start again. Pseudo color, Hardy global. The reason I want to start again is that I'm going to demonstrate now that I can build a long visualization pipeline without drawing anything, which is really the big difference with the software we saw yesterday. So at this point, I will add an operator. I will do an isosurface. And only at this point, I have my isosurface drawn. So by default, I've used 10 contours of the scalar field, and this is what we see on the screen. So this will be the very first test of this visualization package. And as you noticed, I have connected myself to a remote server on Eiger, and this was really a simple button click once this connection was set up. I did not have to do any more SSH on the back to make things happen. Let's go directly to Python and see the equivalent of what I just did on the user interface. If I go to the command menu over here, there is some data I have already saved in previous sessions. So there is, for example, the definition of a vector expression called normals, and it applies on the surface of my particular object. But let's clear this and use the record button. So I will now record everything I do on the user interface inside this particular file. I will delete this object, and I will do again the same operation, add a Hardy global plot, add an isosurface, and draw. There's my picture on the screen. When I stop the recorder, here are the 4 Python commands you need to actually draw this plot. Okay? So really, we don't have to invent anything. We don't have to read the 200-page manual of the Python documentation. Thanks to Brad, actually, who has done the work. But here, it can be as simple as this. Delete all the active plots to start from a clean plate. Add a plot. We give it a type of plot, and then we give it a variable name, and those are additional options to specify the time step which we want to use. And then we add an operator, and we give it a type. And the command that draws everything is the draw plot. There. This is the first example. Now I have a set of variables available in the data set, and I'd like to look at them. And I'm going to use a different plot here. I will split the view. Yeah, they look okay. And in that particular view, which I make active now, I will add a different kind of plot. I will add this parallel coordinate plot, which we saw already briefly yesterday. If I start by adding one particular variable here, the air volume fraction, then I will add another variable, and so forth, and so on, like this. I draw, and there is my, I will try to zoom on this, there is my draw of the parallel coordinates. The reason I revisit this example is that here the user interface, I know how to drive it, and it actually works correctly. So you see this particular icon here. This has enabled the parallel coordinates widgets, and I can now, if you want, you see, lower this particular maximum value, do the same thing here. Okay, what does that mean? This is equivalent to doing a binary composition of Boolean operators. Each operator is a threshold function. So this is telling me I want to restrict this particular axis of variables between those two data threshold, minimum and maximum, and show me in the data set which vertices correspond to this particular threshold. And then I can further, so for example, I could tell that for this subset of data, I have no data available with a range of, this variable is called the radial variable, with a range of radial which is above this particular number. Now this is going to be used by us to do a thresholding operation on the three-dimensional data to display that three-dimensional data. All right. If I go back to my window 1 over here, I will show you a couple of queries which are predefined for us. So here's an isosurface. Actually, before I do this, yeah, actually we can query, that's fine. I will query on the mesh, and I will query for the spatial extent of the mesh. And the answer is -10 plus 10, -10 plus 10. This is because the bounding box here, this particular box, is -10 plus 10, etc. in 3D space. If I now ask for the surface area of this data, what will be the answer? 3D surface area. Yeah, and this is the correct answer, but I wanted to get here using a different path. Average variables related. No, so that's okay. I keep my answer mesh related, 3D surface area. Okay, that's my 3D surface area. So this is the area of the isosurface. Very interesting. It's automatically computed for us. If I now open my pipeline, and to open the pipeline, I have to go to this triangular widget which you see here at the bottom of my screen. There. I will remove the isosurface and draw again. So this is my full box. And if I query again for my surface area, I should find 2,400, which is exactly the area of the sixth sphere, the sixth quadrilateral here of size 40, okay? Of size 400, I'm sorry, because it's an edge of 20. So 20 by 20 is 400. We have 6 faces. The answer is 2,400. This is why it's important that when you query, you are careful with the object that you are querying, because VisIt will give you the active object available. Let's go back to an isosurface, which is this here. And the question that most people have trouble with, most beginners have trouble with, is the following. They would like, in fact, let's open the isosurface and do a single level here. This will be the isosurface at exactly 50% between the minimum and the maximum. Okay? Here's our isosurface. And most people have trouble with the following questions. They would like to color the isosurface by another variable. And they try and they don't make it happen. Why is that? The plot here is based on a certain variable choice, and this variable, I mean, it's very small, it's impossible to read, but this was the variable I had originally selected. It's called Hardy Global. There. If I do a query on that variable, for example, for the min-max, I will get two different answers depending on what I query for. So here's the shape of the output. If I query for minimum and maximum for this variable, I get 1.09, 5.88. This is the original data, which means the 3D block of data. If instead I use the actual data, what should the minimum and maximum be? It should be a single value, right? And indeed it is. It's 3,496. It's exactly the 50% range. So we demonstrate here that VisIt does the right thing. What is happening now is that VisIt uses the default variable here to do the isosurface. So if I want to color the isosurface by something else, I have to specify it right here. So here's what I would do. I would isosurface the variable Hardy Global and say apply, and here nothing changes. And I will change the variable name for the plot module. And I will use here, for example, Chrome volume fraction or something else. Like this. There. So this is the final result people expect. So let me summarize it. Here I have a plot called the pseudo-color plot of variable Shepherd Global. There. And this is what shows in the graphical user interface. And I modify the plot with an operator, which is isosurface. This operator is inserted in the middle of the pipeline. And that isosurface operator takes the variable called Hardy Global. So this is how we do this question that many people ask for. There. I'm going to do now something even more interesting. I will replace the isosurface operator with an isovolume operator. And I will use again here my variable Hardy Global. I will use a minimum of 4. I think that works pretty well. There we go. Yeah, so we have more or less the same. The previous isosurface was at 3.5, if I recall. This is 4. An isovolume is now a set of 3D cells. So they are volumetric cells between the value of 4, which I used, and the maximum. And it gives this. This is quite intuitive as a result. Right? You all follow me here? Okay, good. Now here's a question that is unusual in terms of 3D graphics. We're not talking about colors. We're not talking about scalar ranges. The question is the following. Can you tell me how many regions there are? How many regions there are in this data set? How many little balls we have? We could count them, okay? It's not so difficult because it's simple. I have 1, 2, 3, 4, 5, 6. Here, I don't know, maybe 7. I have 1 here, 8, 9. But then I don't know what's behind, so I would have to go around and, okay, there's nothing behind. I lose the count. Okay, this is not very scientific. You agree with me? This is where we go to query. We go to connected components, and then I go number of connected components query, and I get a direct answer, which is scientific. How many are there? I'll guess 12. 15, okay. So there are exactly 15 components. There are exactly 15 disconnected blobs in this volume. Why is this interesting? Is that now we can do a whole lot of operation on this data, because we're not here just to make pretty pictures. We're here to analyze data. So if I compute an isovolume region here, I want to show how many of them there are. I want to rank them by volume, and I want to do some derived analysis. I want to do some weighted averages, for example, and there, VisIt has it all programmed for us. If I do, for example, a connected component summary, it actually saves it to a file here, so it's not visible. If I do a connected variable sum, there we go. There's my list. So this is not something we do just by looking at it. For each of those components here now, I have the exact value of the volume, okay, for each of those. Yes, you have a question? Connection means they share faces. Because we are on 3D. If you had a 2D example, they would share edges. Okay, good. So now we are getting really into quantitative analysis. We have a way to analyze data, and so my next question could be, I want to analyze things this way, and I want to remove all of those little things that are just the noise in my data set. I want to get to the big object here. How do I do it? Let's see if I remember how to do it. I would use a threshold. So I have a selection, which is threshold. And where's my user interface? There it is. Now, threshold will be the way to select between a minimum and a maximum. However, I need a variable for this volume. It doesn't exist yet. I can compute it, but it doesn't exist. Let's see if I have it yes, I do right here. The mesh object, which was red, was called mesh, okay, with an uppercase M. So I can now use the predefined operator of VisIt called volume on this particular mesh. That's the first thing we need to do. However, if I do this, I will calculate the mesh of each individual three-dimensional cell. I don't want this. I want an aggregate volume of each of the regions. So I'm going to use a couple of other expressions. The connect CON underscore components. This is a predefined operator VisIt, which I have used to isolate those different regions of space. So I define a variable called CC to be the connected component of that particular mesh. And then finally, I want to sum all of the volumes of the individual cells inside of those regions. And for this, I define a variable called total volume, which is the key aggregate. Here's my predefined operator of the variable volume using the connected component of VisIt. So if I go out and display this total volume expression, I should be all set. So in fact, before going to the threshold, I will draw. There we go. And now I will show total volume. And I'm not getting the answer I expect because I miss one more operator. I have to go back to my PowerPoint to explain a particular concept right here. There. When I define those expressions and the queries and so forth, VisIt uses the names that are defined at the very top of the pipeline. So right at this point, when I read the data set, there was an object called mesh with an uppercase M. That was the name. And it carries this name all throughout the pipeline. So when I evaluate my volume here at the bottom of the pipeline, VisIt is actually taking the wrong name. I don't mean to use the mesh object over here, which is the 3D block. I mean to use the mesh object of the ISO volume. This is important because we're going to use this in the exercise. So I need an operator which is called defer expression. Just like in English, defer expression means don't evaluate the expression name mesh at the top of the pipeline here, but evaluate it here in the operator. And let me apply it now to my particular example. I will add my defer expression operator, and I will say I need to select which variables have to be deferred. So the variables are total volume. I think I do faster by typing it like this. Total volume and CC, which is my connected component. And that should be all I need. There we go. You see the difference in the image, right? Red usually means big, blue means low. In fact, this is what we have. From blue to red, we have a volume. So those little blobs here more or less all have the same volumes. It's a low value. And the big red object which I wanted is this one. This is the region of space with the large volume. So in summary, this is what I have done in my pipeline. This is the view of our pipeline here. we have read some data. We have inserted a pseudo-color plot. In the middle of the pipeline, we have inserted an isovolume operator. And we have told this operator defer the expression, the calculation of the volume, defer it later at the bottom of the pipeline. Do not use the mesh object from the very top of the pipeline. And doing this, we are able to draw our regions of space and to color them based on their volume area, which means that now I'm able to threshold by that particular variable. So let us do it. We are expanding the pipeline by using another operator. I will do this. I will add the operator threshold. I will add the variable total volume, and I will say pick everything above 1,000. I don't know if it's enough, but we'll find out. Yeah. So there, I have isolated the one particular region of space which I was interested about. It's the largest volume of connected components in my data. Okay? It's kind of an involved analysis, but it's typical of a lot of data we have to do. I could give you a practical example of this. Libraries, videos. There should be not here. Perché no? I don't have the movie, but okay, here's a fluid dynamics problem which I have visualized this summer. You have the profile of an airfoil, and as you can imagine, we are studying the turbulence on the backside of the wing. Now, on the backside of the wing, we have the so-called vortices. I know there's one of you here in the group from the fluid dynamics group of Professor Kleiser at ETH. This is very important. This is something you could be doing. Vortices are those particular structures, filaments. Here, the job was to extract those filaments, color them, each of them by a different color. So to be able to color them, we have to be able to isolate them, to identify them, and then separate away all the noise, all the small regions of space. So this is what we've done. This is one image, and this is the clean image. You see here, I've removed all the noise. Perhaps, I apologize for the black background, but this should be rather obvious though. Here I've removed the noise. So there is a practical, and I'll find the video during the coffee break. Okay, here's our practical case. Okay, for the exercise, I think that's all I need to show you. We've looked at our pipeline organization here. We have defined the use of the defer expression. If you don't understand it, I'm happy to repeat. So please ask. We've looked at the query. The query is able to give us numbers, numerical values for specific questions we have. And this is what we're going to use for our exercise. Yes? Yes. Command, dismiss. Yeah. Very good, very good. I have the answer. There we go. It's not the most user-friendly interface here. But I have the answer. Don't worry. I will get here. There we go, to what I want. VisIt is made of 5 components, processes. One of them is called the viewer. One of them is called the GUI. There are Python clients. One of them is the server. And one of them is called CLI. CLI means command line interface. This is the Python interface that we are after. And those servers here are called engine underscore SER for serial, or engine underscore par for parallel. When you look at your Unix processes, that's what they're called. So the CLI is automatically launched by VisIt, and this is my interface right here. So I now have a command called write script. That's how I do it. So I have to give it a file name. This is standard Python. Open file name, foo.py, write mode, write script, F. There, I'm done, F.close. Oops. Open a Python file, write script, close the file. It was interesting. I don't know if you had time to see the display. When I did this, it popped up the other window I had instantiated before. It's because when I do write script, I inspect all the pipelines that I have generated. For each of those, I do a query on the operators to find out which options have been used for those operators, such that I can write a Python script that has the full content of my pipeline with each of the options I have carefully saved. Okay? Yes? Wait, I can hear. Yeah, of course. Okay, let's go back to our file. Our file information, as I had shown earlier, has multiple scalars and vector fields available. For example, here the air volume fraction gradient. For example, as a scalar field, shepherd global, radial, etc. And as you can see, for each of those variable names, there is a mesh name that is associated with it. So for example, the radial scalar field is associated with the grid object called mesh, whereas the HG slice variable name is associated with the grid object called mesh2D. So I can have multiple grid objects with multiple sets of variables. All right, so Those are my variable names. When I go to my expression editor here, here I'll just start with a new one. New expression. There's a bug. As you see, I clicked once and I got two names. This is a well-known bug. Somehow, it's not critical, so nobody has time to fix it. I'll give it a name. Whatever name. So, course. Here I have the choice between making an expression that has a scalar, vector, tensor, symmetric tensor, or a remesh or curve mesh variable type. Let's say I want to do a scalar field. I use this. And now I'm free to type anything I want, reusing the names of the variables available. And not only that, but a set of predefined functions. So if I, for example, here, let's say I have a scalar field, I can compute the gradient if I want the gradient. So where would the gradient be? Most likely in mesh. No, not in mesh. I don't see it. Materials, no. Array, no. Tensor, vector. Oh, it's just under. Why don't I see it? Miscellaneous, gradient. I click on gradient. VisIt puts the parentheses, and I just have to insert my name here. So I insert variable name, Hardy Global, there, and I apply. At this point, I have a new variable called course. Its value is the gradient. Wait a second, the gradient is not a scalar, it's a vector field. So this would be good. Actually, if I make the mistake, the first time you try to use the operator, VisIt will tell you, wait a second, gradient is a vector field. So I go out and change that to vector mesh, and I apply. Okay, this is one type of a expression. There's another type which is very interesting. I have to try to find a data set. If you have a time-dependent data set, then you can do expressions comparing time steps. For example, if you want an average, if you want a moving average of 3 time steps through time. The current time step, the time step before it, the time step after it. You can write that into an expression, and as you play the button play, VisIt will display your data doing the average of the 3 time steps there along the temporal axis. This is interesting, so I'm going to try to load to find a time-dependent data set, which on that machine I don't know where to look. VisIt projects. Oh, actually, there is one here. Results, good. Silo. This, I'm going to use the data that we're going to use for the exercise. There it is. All right, let's delete this. I've now opened a new data set. This data set has 1,467 time step. There. It's a pretty long list. I don't need to look at it. I will display the mesh. I will display the pressure variable. Okay, so I'm actually starting to show you the data we will use for the exercise. Here is my blood artery, and here's the pressure. If I play the button now, it's pretty slow. I don't want to do this. I want to go echo to a particular time step. You can see that the coloring is changing, so there is activity here going on. In fact, perhaps we don't see very much. So what you'd like to see is the difference between one time step and the time step before it. And this is done with the expressions. So let's see how this is done in this particular case. I will go to data level comparison. This is a menu that is all programmed for us to make things easier. Let's look at the choices we have. We can compare data that is stored on different meshes, or we can compare data between different time slices. So this is what I will use. I click Next. This is the source of my data. The target mesh is this indeed. I will use the pressure data. I click Next. And here are the choices we have. I want to specify an absolute time or a relative time. Relative time would be, for example, -1, which would be the current time step minus 1. So I will use exactly that, -1. Oh, actually, let me think here. A relative time index -1. Yeah, this is good. Next. Here's another question. When I do this evaluation between different time steps or different meshes, what type of interpolation should I use? I have two choices. One of them is connectivity based, which means I use the IJK indices with a Cartesian grid or the cell index for an unstructured grid to get data from the other object. Or I can use a position-based interpolation. Position-based would be very useful if you have the case of two meshes which have completely different type. Perhaps you have an unstructured grid solver and a Cartesian grid solver for the same domain. The vertices don't match, but you are still able, using the position interpolation, to take the vertices of this object, move them into this particular space, and do your interpolation. This would be the case. Here we have a mesh that is constant in time. So I will use the connectivity-based CMFE. I will explain what that means, which means it's much faster if you use indices. CMFE, this big name here, means cross-mesh field evaluation. It really is, it's really what it is in English. We evaluate field across multiple meshes. I say next. What do I want with it? So I have now a name of an expression. I will call this diff. And I will simply place it. Yes, I'm happy with that. Okay, nothing has happened here except that I have a variable now called diff. And let's look at the name of this, the expression for this variable. Diff is a special kind of expression It's the connectivity, so CONN, connectivity-based cross-mesh field evaluation of variable pressure on the particular object called mesh at time step current step -1. There. This is not exactly the difference. This is the value of the previous time step. If I wanted to do the difference, I would have to do, so let's see, let's watch what I type here on the screen. I will have to say pressure minus the previous time step. So now I have the correct expression to show. And in fact, at this particular time step, which is whatever number 798, if I display my variable diff over here, was unable to change because it was invalid. The parser expected more stuff up to the end. Oh, it's missing. Yeah, it's missing a bracket. That's strange. Expression, bracket. Where does the bracket go? That's a good question. I think it goes here, but I'm not sure. Apply. Draw. Diff. There we go. I don't know if I deleted the bracket by mistake or if something happened. So this is showing the difference between the current time step and the previous one. If I now move my time slider to any time step here, it will again calculate this difference. But if I go to time step 0, there's no previous time step in that case. Let's try it. I go all the way to 0. It gives you a nice warning. There's no such time step, etc. there. So anyway, it doesn't break. The difference is 0 because we are at the very first time step. Okay, this was a little bit ahead of what I planned to show you because I wanted to keep it simple. But people ask me questions about expressions. I gave you the full discussion, and I think it's actually very powerful. So in summary, and then we can take a coffee break. In summary, expressions are a way to define new variables of any type, scalar, vector, tensor, whatever, reusing a set of predefined operators which you apply on the name of the variables available in your data set. That's the first chapter. The second chapter is there's a special collection of expression which is specific for time-dependent data, where you can do multiple types of expressions, averages, differences, difference between the current time step and the first time step, so it can be relative or absolute. You have quite a bit of flexibility in the language. If I finish up with looking at the information on my data. So here are all the file names. I kind of expected that. I cannot browse to the end. Oh, actually I can with the... Okay, here's the mesh called mesh, nothing unusual. This is what is available for the exercise. We have two fields. One of them is a scalar field called pressure. One of them is the velocity. Guess what? VisIt has already done a lot of work for us. It has predefined particular expressions. A lot of them based on the mesh quality. Fine. And Oh, unfortunately, I cannot browse to the end because of the limited pixel resolution of my screen. I will tell you what is predefined. The pressure is available, so gradient of pressure is already predefined. Velocity is available, so vorticity is predefined. The gradient of velocity is predefined. You can access each of the components of your tensor, the gradient velocity, already as variables. They are predefined for you. In addition, because we have a time-dependent data set, there are predefined expressions such as, for example, the derivative of your fields, which are calculated using a standard stencil expression. So position to the right, position to the left, divided by the cell size, etc. in 1D. So those you can have access to. That's a good question. So the order, I think, would be simple trilinear interpolation. If you wanted something more fancy, it could be done with a Python filter. It could be programmed exactly in. There are exceptions to that. There are some specific data format. One of them is NEC 5000, for example, which is this spectral code we use here at CSCS. A number of astrophysics code have that. A number of fluid flow codes have that, where you can specify to use the shape functions, approximation routines of the code to do your interpolation. This is true for the evaluation of gradients and so forth. It's also true for the evaluation of streamlines. In the streamlines menu, you will find some options which are specific to some solvers. This is the case where they do the proper interpolation related to the solver. This is all available if you import a time-dependent data set. Yeah.
I mean, the operators that are relevant for that model or whatever.
Yes.
When does that become available?
It will become available because the reader recognizes that you're reading data from a specific solver. And then it triggers inside VisIt, it triggers a set of flags. Yeah. Okay. Before we break, I promise we're going to break in a couple of minutes. I'm connected to Eiger here, so what's the magic? In fact, if I show compute engines, it shows that I'm connected to Eiger, one node, one processor, 0 GPU, really basic stuff. How did that happen? It happened like this. Under options, you will need to define a host profile. Actually, I have a host profile created already for you, so you'll just have to copy it. So just follow what I'm showing. I have here the host profiles for 3 machines defined. Let's do that at Eiger. This is telling me that Eiger is a machine with a nickname called Eiger, a remote host name called this, a particular path to the VisIt installations, which is apps Eiger VisIt 2.7. This is where I have installed the software myself. I want to connect to it using the username Favre. I want to use a data connection through SSH. Here, actually, I'm at CSCS. I don't need this gateway. It probably works without it. This is what I use when I am at home. So at home, I go through ELA and then to Eiger. So here, you define the host name you need to connect to and the path where VisIt is installed. And then you define some launch profiles. On Eiger, we have two sets of Slurm queues. One of them is called STDM. The other one is large, so standard and large memory. Let's look at standard. Here's what I have. In the launcher arguments, I have it. Those are the arguments that are passed to Slurm. I want 23 gigabytes of memory. I want an exclusive use of the node. I want a particular reservation. And I want CPU binding to sockets. This is all the stuff I have prepared for you. I don't have to justify all those choices. Under advanced, I don't have anything. So here, I specify that I want to use S1. I specify the name of my queue. The default number of processors is 24, 2 nodes, 59 minutes. And that's all I need. So dismiss that, delete, 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 close, close. Okay. The second window is here. I close it, close, there. Here I've got nothing. How do I connect to it? I open a file. Instead of choosing the local host, which would be your desktop, I select the name Eiger there. Well, here it didn't ask for my password because the connection is still active. But let me start from scratch. Here's VisIt. Open file, Eiger. Watch carefully. It should pop up here a window for a password. You give it your password. There. Now I see the file system on the remote machine. And I have some predefined path here. I can go. Oh, actually, this was the one that didn't work before. No, it worked before, yeah. Noise.silo. No, let me open something more interesting. I'm here. You can try this one too. Multi-UCD. I say OK. It brings up this particular window. Do you want the standard memory? Yes. Do you want 24 processors, 2 nodes? Yes. I'll just say OK. And this is what gets printed on your screen. This is a long command. It's being sent to the Eiger machine over there, telling it to run with 23 gigabytes of memory, etc., and to open a compute engine. There, I'm connected. Let's color by the processor ID, just like we did yesterday. I will need to define an expression for it. I think it's predefined in my menu. It's called proc ID. Proc ID is proc ID of mesh 1. It's all set. I do an add pseudo color proc ID draw, and there is my mesh. The color bar goes from 0 to 23 which means I have exactly 24 processors which are visualizing this domain. There. I'll stop here. We'll do a coffee break. You can ask me questions during. Very good. So let's start again. I have here this display of the mesh loaded by multiple processors. And they were in if we look at the computer engines, I think they've disappeared because I lost my connection during the pause. But the data is local. I need to find the name of the mesh. If I look at file information, the mesh name is right here. It's called mesh 1. I need to define an expression. Call it whatever you prefer. I call it proc ID. I use a predefined operator called proc ID, and I give it the name of my mesh. Now, if you don't remember this name of the mesh here, like this, you could always go to the insert mesh name, and here the mesh name appears in the list. So there's no guesswork to do there. If you apply, and if you display, if you plot your data by the processor ID variable, then that's what you get. All right. Let's go to our exercise. How many of you intend to use VisIt directly from their laptop? Good. This is a good. Almost all of you. All of you? Almost all of you. This is very good. We're going to need one file, which is the configuration file for the host profile. And I have made that for you. I need to add a special keyword for it, and then it will be ready. That particular keyword is for the reservation class. So give me a second. On Eiger and on every other machine at CSCS where you will run VisIt, there is a directory called apps, the name of the machine called Eiger, the directory VisIt there. And in here, on most machines, you find one code called parallel-run.py. It's a Python script to test, and you find the parallel-run.sh, which is the Slurm script to run in parallel. So if I look at this particular example here, I would see that I'm allocating 32 tasks, 4 nodes, etc. And I run VisIt with the option -no window, -cli, this is the command line interface, -s, the name of the Python script, -np, the number of tasks to use, -nn, the number of nodes, and then the command s1. This will work at the condition that your host profile is set up. And we have a host profile defined right here. Let me simply add the keyword which we need, mem. All right, right here we need reservation equals course. Pardon me? Yes. All right, so in this directory, apps Eiger VisIt, you find the file called host_Eiger. You need to place this file in a particular folder. This folder is called, under your home directory, .visit. And under that directory, a subdirectory called hosts. And here you will see, for example, for myself here, I have a number of hosts predefined. I have one for Castor, one for Daint, one for Julier, Pilatus, Rosa, Rothorn, all the machines here at CSCS where VisIt is installed. For the moment, concentrate on host _ Eiger. So you need to copy this file in the home directory of the machine where you will start VisIt. So if it's your laptop, it needs to be copied on your laptop. If instead you're using a VNC session, this will be on the home of Eiger /.visit/host. And as you do this, if you do this correctly, when you start VisIt, you should have predefined here under options, under host profiles, you should find the Eiger profile. So this is the first thing to check before attempting any visualization. You need to have this host profile predefined. For those of you who have started to edit it by hand, it's not so difficult. You need to tunnel the data connection through SSH. Here you need to be careful with the path to the VisIt installation. This is exactly apps Eiger VisIt 2.7 and there's no, pardon me? That's fine. If you copy it to the machine, you don't need to do this. I'm showing this for the people who attempted to do this interactively on the machine. But I can pause and let everyone copy that host file to your home /.visit/host. Okay, this is the file. And host is a subdirectory. It's not a file called host. Okay, so if the subdirectory does not exist, you create it. .visit/host is a subdirectory where you will store multiple host configurations. Yes.
Maybe two related questions. So where do you specify username?
So username is, so that's a good question. Once you copy this, you launch VisIt, the default username will need to be edited because it's my username. If you go to the host profile graphical user interface, you will find my name, hopefully, and you change that to your course ID. Let me start it again here, and then we will see. Here, under host profiles, you see, once you load it, here the username should be set to my name as an example, and you change that to course 0, whatever you have. You apply, and then the first thing to do is to actually save your settings, so that you don't have to do this multiple times. And it will update the host Eiger file that you have privately copied to your directory. There, those are the four things you need to do. Once you run VisIt, change the username. Oh, you can change the username already before you're running VisIt. Yes?
So I continue,
Yes.
and then I open VisIt. Right?
Okay. Here under options, show me the host profile. There, it's all there, good. I recommend trying without this option actually for now. Do an apply. Okay, dismiss. Then you can go and open files. Open, file open. Okay, and here instead of localhost, you choose Eiger.
Here.
Okay, return. Okay, then put that flag back on, the Ella flag. But somehow
I tried it even with that one, but it didn't work. Maybe should I do it fast?
okay, this is fine. Yeah, dismiss. Now do an open. Do you have it here as an option to choose Eiger? There we go. Okay. Yes.
This happens
Ah.
for quite a while.
270. Okay. No, but that shouldn't be much of a problem. Okay, something is wrong, obviously. I give to set the shot. Here, I'm hesitant. It might not make much of a difference. Save settings, open. Yeah, here we're stuck. Let's run again. All right. Good.
Yeah, sorry.
Network is unreachable. Aha. This is why you're having an error. Added CSCS is unreachable. Let's try again.
Is that maybe because we're all trying to do it?
you should use CSCS, not ETH.
Okay.
This will not work with ETH. Make sure you are using the CSCS wireless permissions. There's very strict rules about accessing machines and different Wi-Fi's, and make sure to use CSCS, not ETH, even though you are an ETHZ employee. Yes? Excuse me, is it a problem of permission, or is it...
It's like this. I go here. Do I hide it? Thank you.
Does it ask for your password 2 times? I think that's the problem. I think it's the problem. But maybe if it asks you, yeah. Yes, you can disconnect. Yeah, it's probably safer from yesterday. Okay. Doesn't work for a single person. It works for you.
Log in and have the username. So I clicked add the user, and I could type in the username, and then I could again ask for the password, and then it shows the username.
At which point was that?
When I added the file.
Okay. So fine. So let me describe the problem, because some persons are ahead already. I don't want to slow them down. And then we'll go back to the person who have problems connecting. Here's the description of the data. We have pressure, and we're going to show pressure display, velocity glyphs. We're going to do some picking, some streamlines. We're going to compute the flux through a surface. Okay, the flux is the amount of fluid traversing that surface. And then we'll do some transient analysis doing the following things. The data was actually calculated by one of our staff members here. This is Gilles Forestier, calculated at EPFL on the IBM. This is the result of a solver called Life V or Life 5. I never know which one to say. So here's the first task, to do display the mesh. Not only the pseudo color display of pressure, but I also want to see the mesh like this. You see that we have a tetrahedral mesh available. The data files are right here in the project course directory. Okay, thanks. First thing to do is do multiple plots, update the time slider, and you should see an animation of your data. So pseudo-color plots and vector plots, those should not pose any problem. We've seen a demonstration of them before the break. Now, here's the real problem. At the base of the data set, I want you to draw a slice here, a perpendicular slice, which is oriented in the positive y direction. Okay, you see here my y-axis, and I want you to do a display of velocity magnitude. And then the question is to select the point in space where the maximum of velocity magnitude appears. But this shouldn't be guessing. You shouldn't say, oh, just because it's right around here. I want you to use the query menu to look for the maximum of velocity magnitude on that particular slice of data. And you're going to use a slice intercept at y equals 3. And once you do this, and if you query the correct information, you should get this x, y, z coordinates, which we will use as the location for a seed point to draw a streamline. So if I have the picture here, okay, here we see a number of streamlines. As you can see, they all start from the base of the domain here at y equals 3. Here I have a circle of seeds and different time steps. Now, once you do the single streamline, it should not be much more difficult to draw a circle of seed points centered around the same vertex. Here, I use the same coordinates origin. Make sure the view normal is pointing up in the y direction. I use 12 seeds around the circle, and I do my streamlines. There, that should be quite a few things for you to work on while I look at other people's display. And if you haven't understood the task, please ask me again. Okay. Are you connected now?
No, I downloaded the data.
Okay, that's a good solution too. So this user here was saying that he was connected, that he had to. Oh, what is your problem then? This. Please connect at all. Qui?
Yeah, it's waiting for the metadata server to start, but it doesn't.
Are you sure? Did you type a password already?
Only once. After I deleted config in .ssh, he asked for a password.
Okay, okay.
But this doesn't progress any further.
And you, what is your username?
Course
08.
Yeah.
Let me see, just as an example. So the person who's connected, this is course 15. This is you, eh? Okay. All right. When we have debug, when we have connection problems, there's an option to, you need to quit VisIt and run the option -debug 4. And this will output some debug logs which we can inspect to understand the reason for the problem. Okay.
It asked me for my password twice, and now it's this.
All right. Why does it keep asking for Anna instead of course?
That's a good question.
And what password did you type here? The password for Anna or?
Of course. I mean, Anna is not the thing that it says.
Ah.
But in the IGA file, it says my course 18 username.
Yeah, I've seen this message hundreds of times, so I know what it says. So we quit completely, and then we see if double control string. We see if any log files were created.
Minus is in there.
No, where's the star? You type
I see.
star log, log. Okay, and look at a.md server number 4. Okay.
Daarvoor is afgemaakt.
Adding plot. Signal exit cint. Well, maybe this is because I did Control C, so it doesn't help us. And you're on IGO now here. Go.
Wrong
Yeah, I understand, but you should see if log files have been created on the other side.
I also can't. I mean, I can't directly connect onto IGA. Is that a problem?
Certainly. No, try
Because I have to go via
IGO.login. No, I'm sorry. The login is only for the name with the single with the numbers. So IGO is correct. Why not? Let me ask Angelo. Ma Normalmente possono sì o no accedere a IGO direttamente con l'SSH?
CSCS secondo me. Perché lei non ci riusciva passando da IDAS.
Ok. Tu sei riuscito a connetterti? No? Perché no? Usando il tuo account di start.
Non so cosa sbaglio, cosa c'è.
Fammi vedere.
La rete CSCS.
Fa vedere lo straw file. IGO, metti qua.
Ho messo qualcosa.
Aspetta, sì, ma però qua. Ok. Bene, questo sì. Buono. Parallels di advance. Qui meno reservation. Return, apply, dismiss, save, open, IGO. Ah,
Altri sono i porci.
ah. E
Mi sono copiato sto
Ah,
insieme.
io ho un'idea.
Tra l'altro da qua si è bloccato. Devi uscire.
C'è una pagina su Iger,
Fare CTRL C.
così. Sì, proprio il blocco. Là là.
Devi andare sul...
Ok, questo è Iger. Mi chiede se devi avere il module load all'interno del bash. Ok, one tip. When you run on Iger, you need to have a module load. Of course, when through the interface here, we don't have any option to type anything at the shell prompt. I would suggest you edit your bash rc file on Iger, and you insert the command module load VisIt inside the bash rc file, such that when VisIt connects to Iger, then it knows where to find VisIt. And that might help. Yes?
Said there were scripts placed in our own directories.
This was something I was supposed to explain. I can explain it now. When I wrote VisIt under the command option here, I don't know if you've noticed this morning, I have 8 different tabs here, and each of them can contain a particular script. So something easy to do, and this is what I had written in the notes. Somebody pointed that out. Echo. For this tutorial, I have placed the Python scripts in a convenient place. In the same directory, .visit. All right, everybody. We need to continue with our exercise. you've understood the first part of the exercise, which is to create a slice on the mesh, plot the velocity magnitude, query for the position in space for the maximum of velocity, use that as the seed for a streamline. And from there on, you've done 90% of the exercise.
You get the location from the query, you have to copy it. It's not automatic.
Okay, so yes, this is true. In the graphical user interface, it's not automatically connected. You have to copy the XYZ coordinate that you see, copy and paste it into the widget for the streamline. And careful here, when you copy this, there is X, comma, Y, comma, Z. You need to remove the commas from, it needs to be X space Y space Z. Yeah, this is a graphical user interface artifact. However, remember, we are always focusing on creating a Python script that will do our visualization. When we write the Python code, the equivalent Python code, we will be able to pipe directly the output of the query into the streamline Python object options. So then it becomes really automatic. Okay? So do you have problems in executing this? Yeah.
When we start like a circle of different splits,
Yes.
we have to specify a radius of the circle.
Yes.
Is there a way to measure how big is the slice?
Yes, there is. There is. This could be automated via Python. Let me be frank. I don't have time to explain it this afternoon. There will be. We would have to do a little bit of a manipulation, but this certainly can be something that can be automatized. You know that for any object, any geometric object, we can calculate its volume, its area, the distance between the physical distance between one particular vertex and another. So doing all this, doing those calculations, we can extract the radius, the mean radius, for example, of the surface object, and from that derive the information we need. Yes? Where is the Python script saved? It's most likely saved in, so first of all, it's saved on the client side. Okay, not on the server side. Am I right? Yes. It's client side, so you need to look for it on your laptop, not on the, and it would be most likely written in the directory where you have started VisIt. So look right there in that initial folder where you started VisIt. Otherwise, when you write the script, you can specify your full path, an explicit path of your convenience. I don't see any other person raising their hand, which means I'm assuming everybody has that first part running. So highlighted in red here, make sure that when you query the actual data, which is the slice through that mesh. This is really the only difficulty at this particular moment. Doing a circle of streamlines, the difficulty here is to make sure that the slice here points in the up direction, the vertical direction. So I changed the default to 0, 1, 0. And then unfortunately, the graphical user interface calls this the up axis. But really, for me, the up direction is the normal direction. So 0, 1, 0. And then I use a radius of 0.12. This is what you should have on your screen when you have a bundle of streamlines generated. At time 0, we have this. At time 99, we have this. Time 199, this particular object. So remember, the streamlines are lines that are tangent to the instantaneous velocity field. There. Now, the true behavior of this is a transient evolution of the flow, so we should be calculating path lines instead. And it's not much more difficult, but perhaps I'm skipping a fundamental step here. Computing the flux. Oh, I guess you haven't done the flux yet, have you? All right. What do we need to compute a flux? We need a surface, a velocity field, and then we need the normal to that surface. And then the flux is an integral calculation using that normal vector, and you doing a dot product of the normals and the field vector. So here's an illustration. We have a slice. The velocity at this particular time step, I forgot which one it is, it doesn't matter. The velocity vector is pointed in that direction there. The vector normal should be a single normal here. It's constant because we have a perpendicular slice pointing in the y direction. So we know that this is correct. We're displaying multiple vectors because this is how the default glyph vector shows. Here is our summary in Python. We're going to plot, do a pseudo-color plot, and we have predefined an operator called flux. If you look carefully through your graphical user interface, and I need to do it for you here as well, you will see when I start VisIt, when I add a pseudo-color plot, you will see that I have the explicit option to go to a flux operator. Let me connect rapidly to Eiger. When I open the connection to Eiger, the default is to give me 2 nodes, 24 processors. However, I know that for this particular data set, it is wasteful to use more than 1 processor because VisIt does not know, in this particular case, does not know how to partition the data among multiple processors. So I will simply say 1 and 1 here. That's all I need. And it would be just wasting time to try to do more. Ma no, non ci credo. Ok. Fine, cancel this. Pseudo-color, let me show you the graphical user interface. That's all I am trying to do. I have here pseudo-color. I have the normal variable names, and then I have here a few operators. You see? So by doing this, pseudo-color, operator, flux, mesh, that's how I predefined my operator in Python, and this is when I show now my my PowerPoint, I get exactly the same name here in my command, add plot, pseudocolor, operator, flux, mesh. I add the operator slice. I defer the expression of the normals. What is the normals? Perhaps it's not available if I look at my graphical user interface under expressions here. I have a predefined operator called cell underscore surface normal. However, if I apply this directly to the object, what will I show as the normals? I will show the normals to the global mesh. So in this particular case here, I would have vectors pointing in the perpendicular direction like this. Over here, pointing in this direction. Just like in the computation of the volume this morning, we need to defer the evaluation of the vector normal such that it applies not on the global mesh, but it applies exactly on this particular slice. So this is why in my Python pipeline here, I have an add operator slice, and after it, I defer the expression of the variable name normals. At this point, I take a flux attribute object. Number one means take the current object. When I do an add plot operator flux mesh here, I instantiate a flux operator. So I want to get the attributes of that current operator. I select the velocity field as my argument, and I will get an evaluation of the flux of this vector with this particular normal on that particular slice. I recommend you try this. Via the graphical user interface, you should be able to instantiate your, so you'll need a couple of things. You'll need the evaluation of, you need the expression normals. So here, I call it normals. Make sure to define it as a vector mesh variable. In the list of insert function and the mesh, presumably, or mesh quality, mesh, no, and the cell, no, on the, where do I find it? There we go. Under miscellaneous, you find cell surface normals, and then you give it the name of your mesh. So this is your expression to start with, and then when you add your pseudocolor plot, you select the operator flux with the mesh. I'll have to attempt to connect again. To continue the demonstration with you. in your flux operator attribute, you'll have to select a variable name for the flow field. Otherwise, the default, it might not know what the default is. So make sure to double-click here on the flux. Make sure to select the flow field as velocity. Okay? The slice needs to be done at y equals 3. So I think the default is to select the y-axis. It's on already. And here you intercept with the value 3, which really means altitude or elevation 3 along the y-axis. And then the default might be, I don't remember, to project this particular slice to 2D. You need to turn that off. Yes?
No, I thought the slides were the output for the velocity vector.
Yes? That's correct. Yeah, you want the slice to be connected under the pipeline for the pseudo color plot. So there are two independent pipelines. The streamline was something else. You need to create a new pipeline, which is a pseudo color plot of the flux operator using the slice as a surface.
That I've got two slices.
That might happen because by default, if you look here on the graphical user interface, you see here you have two boxes: apply operators to all plots, apply subset selections to all plots. Make sure those are turned off. to verify that you are computing the right things, you should have, you can display the surface normals, okay? Doing this is as simple as, let me do an example here, vectors. So the vector is a plot. I say add plot vector. I select either the normals or the velocity, and I slice it at the distance y equals 3. As you can see here, this is equivalent, saying arbitrary or y equals 3. I defer the expression with the name normals. Actually, this is my operator. I was looking more at this one. This is the one, slice vector. It's even simpler. This particular one is a plot of velocity with a slice. Let me turn it on and off. Okay? Those are the particular green vectors I see on my slice. The other one, I have two operators here. Here's the second one. Let me turn it on and off, hide and show. Okay? This is the one where I slice and I have to defer the expression of normals. Let me show you what happens if I don't include the defer expression. I get this. Well, actually, in that case, I wouldn't even be able to do it because it needs a surface. I need to add an operator, geometry, extract surface. So where do I find this? Under analysis, under geometry, external surface. It still doesn't like it. Still doesn't like it. I don't believe it. This is strange because I'm doing exactly what the error message says, and it doesn't want me to do it. So I'll forget about this particular example. Now the flux I have computed here. If I turn off, just to make it a little bit easier to see the mesh display, there. This is my flux. You can see that the coloring now is constant over the surface of each triangle. In fact, the flux is computed on a cell basis. Okay? Because it does this, this dot product of the normal and the velocity at the center of the cell. And if I choose the correct object at the very end, so this one, I can now query for the value of the operator. I'll do a query variable related, variable sum. I didn't like that. Normals is here. my flux was computed correctly. There's my flux. Okay. We have a negative flux, which is most likely caused by the fact that the slice here, the triangles are oriented pointing downwards. Okay, this will depend on the mesh object you're using. When you slice it, it can be that the ordering 0, 1, 2 of the 3 vertices of each triangle points in a clockwise order or in a counterclockwise order. And this is why we can get a negative flux on this particular object here. I would have to look at this in more details to flip this around. Yes? Yeah. The expression is computed like this. Normals. What is important is to define it, to define it here as a vector mesh variable. And then over here, we use the pre-defined operator. Oh, here again, I have a problem with the user interface. There we go. Cell surface normal. Which gets created, and then here you insert the name of the mesh, which you can get from the menu. All right. Yes. To draw it. So let me start all over here from a blank page. If we can look at the script, so there is my definition in Python, defined vector expression normals. It's the same thing we do via the graphical user interface. This is my first line here. To draw the normals, we do an add plot of type vector with the name normals. With the particular, here I gave it 14 as the number of vectors to draw. And we set the plot options. We add an operator slice because we want those normals to be only on the slice attribute. We add the operator defer expression with the name normals. And then we can draw the plot. So if I execute this all together, it will do exactly this. You can count one of those blue vectors. There are exactly there should be 14 of them, because that's what I set up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why am I not seeing 14? Vector, yeah, fixed number 14. Maybe there's, oh, actually, it could be that some of them are on top of each other and we don't see them. The mesh is this object. Let me get rid of this. In order to see the triangles on the slice, I've done this particular object, which is a mesh and a slice. So if I turn it on and off, it shows me only the outline of the triangles. this particular display here is the display of the velocity magnitude. So I turn it on and off. Oh, why is it not reacting? There we go. Yeah, yeah. So this would be. So to fix this, it shouldn't be difficult. You go to your slice operator here, and instead of intercepting the slice with y-axis and 3, here you can give it a 0 and -1, 0, and that will flip the normals. Now, I wanted to point out to the solution for us to kind of move ahead here. That particular, in the course directory, under Python, VisIt, and rhythms, you will find the script called flux. Now, the only thing I've done is to comment out the open database. That gives you the flexibility to open it wherever, if you copy it on your laptop, or if you use it from a different directory. This assumes the data has been opened, and then everything in between does the full generation of this particular script. Okay. Let's see. This is complete. So you're welcome to re-execute this particular script using the command line interpreter. Now, quickly, I want to go to another type of display. I will simplify this to the bare minimum, okay, and look at the picking. There are a couple of options we haven't seen today. Those two which I'm using here with my pointer, +Z and +N. This means picking, so zone peak and node peak. If I do a zone peak, for example, right here, okay, let me show you the error message. It's nothing in peak requires a non-hidden plot. So this is the error comes up just because I haven't set the active object appropriately. This should be my active object, and at this point I can do a peak. So what happens? I wonder if you can see it, but a label has been put at the place where I clicked on the, let me put it in the yellow region. There we go. We can see B. Every time I click on the screen, it will show A, B, C, D, and it will open a pick window, which is right here, with the information about what was selected under the cursor. So under the cursor, I can see that the position in space was this particular XYZ, the node ID was this, and so forth. There. Now, if I were to draw the evolution in time at this particular point, I would get a certain type of data, and I will show you that data, and then we'll look at the script. That data I have pre-computed computed for us, and the Python, so you can load it as well. There, it's called pressure curve. If I look at this pressure curve data, what is it? It's a 2D, it's a table with the first column being the time index and the second column being the value of pressure at that particular node index. All right, let me select it, I double click on it, and then I draw it as a curve because it's 2D. If I draw it as a curve like this, here's what I have in my display. This is showing us exactly the heartbeats. So this is connected to real physiological data. The simulation was done with, I think, a heartbeat of 60 beats per minute. And we see here just one heartbeat, then a second one, and so forth. So the full simulation actually shows those different heartbeats. Now, if we look at the corresponding script, you'll see that it's really quite simple. I forgot the name of it. Picking. Picking is the name. I open my database. I add a plot of pressure. I define an arbitrary node index. Okay, in this case, I just pick that particular number here. Here in Python, I open my file name in write mode. For all the time steps available in the data set, and this is available in Python via the command, via the operator time slider get the number of steps. I set the time step at that particular index. I query for the time. And then I do a pick by node. The exact same operation I did via the graphical user interface using the mouse cursor to pick on the surface. Here I can pick with a node ID. And I get, as a result, a dictionary, a Python dictionary, with an index pressure for the variable that I'm looking for, and I can write this to a text file. How do I execute this? I do it like this. So let me remove completely this file so that you can see that I'm not cheating. I have a Python script. I simply need to do -VisIt. I run without a window, no window. I use the command line interface. -S, I give it a file name, and it will now calculate everything. You see, for every time step, it will iterate through my data and construct the plot data set. I forgot there were so many time steps. There, anyway, this demonstrates how I can do an automatic analysis of my data. If I go back to my 3D display here, this is the final output, and I think I've actually closed VisIt doing that. I clicked on the wrong button. All right, that will finish my demonstration then. Here we're still running. It will run until the end of the data set. Yes. Yeah. I selected it via the graphical user interface. So when I picked on a particular place on the graphics, it actually gave me the ID of that node. I just picked the first one that looked interesting for me at the surface of the data set. There, I can simply quit this particular thing, and as you can tell now, my file pressure.curve has been created here all the way to time step 1.13. If I were to load this in VisIt, minus O, like that, I would get back to my curve data set. I add a plot called curve, and I draw it. There we go. Okay? So from 3D, we've gotten all the way to 1D inspection of one particular node ID on that mesh. Let me go forward a little bit in the presentation. This we've seen already this morning, actually, using the expressions. We can look at multiple time steps, compare one between one time step and the time step ahead, do aggregation. We can do also some other fancy operation. Let me show you the expression menu again. Here's the expression menu. I have to click new just to make this available. If I look here at the very bottom of my selection menu, I have time iteration. And you can see the options I have. Given a time-dependent data set, I can do any of those operations, an average over time, but I can also do some query. For example, find the first time step where a particular condition is met. And if I click on those, let's do it here. For example, first time when the condition is true. There. You see that VisIt gives you a template with the operator, first time when condition is true. Here, it's your job to put the condition. The condition can be pressure greater than a particular threshold. Here, as you can see, it uses the operator position-based cross-mesh field evaluation. If you know that your mesh is static, you could replace this to a connectivity-based evaluator. And then finally, you give it an option for the first time index, the last time index, and then the stride. Using that as a query, you run this in batch mode. It will go through your entire data set series and find for you the particular time step where the condition is true. So that becomes quite a powerful expression. I will go back to the menu here to look at other examples. Find the minimum over time, maximum, sum, etc., and so forth. All right. When we're using multiple time steps, oftentimes we'd like to see one time step and a different time step together on two windows, two separate windows. This is trivial to do in VisIt. This is why I recommend VisIt. Yesterday I told you that with ParaView it's impossible to do. With ParaView, whatever views, they're always fixed to exactly the same time step. This is because the viewer drives the execution of the pipeline, and by design, the viewer holds the time step in ParaView. So you cannot do like this side-by-side comparison. In VisIt, instead, the time slider is independent for each of your window. There is the script I executed earlier, and you execute it with this particular command here. Now, in all of those small Python examples I've given you, there's no connection to a parallel server. So I run it at the command line. It uses the processor that is available, and that's it. But we have actually just two lines of Python to run a script in parallel. One of them is called Open Compute Engine. And this is where you say, I want to open with 24 processors or whatever on another machine. This will not be saved automatically by VisIt when you ask it to save the script. So you need to experiment with it, and I would help you do the things here at CSCS to make it available. I can show you the syntax, which I was planning to show you yesterday. It's available only in ParaView, however, but it's in your notes. In the notes yesterday, oh, did I put that at the very end? There's a link that I have put. If you go to the wiki, you can find representations of this technique, which uses a texture of noise which is advected, which is convolved with the velocity field to show a really nice display of velocity. This would be something you could use also as an alternate to this type of display. Line integral convolution. Yes. Meshes, so no secrets now. We all know. One thing we didn't mention yesterday is that besides this standard type of meshes, we can have also molecular type data. Okay, so this is a full first-class citizen in VisIt. I can load data in PDB format, in Gaussian format, in GROMACS, etc. All those standard outputs of simulations. There will be the difference between data that is stored at the cell centers and data that is stored at the node center. And that's about it. This distinction between storing data at the center of the cells or on the vertices. However, just yesterday evening, there was a commit of a new code into the SVN repository of VisIt to do streamline where data are placed at the midpoint of edges and at the midpoint of faces on 3D cells. So this could be very interesting. I know several people have asked me for that in the past. So data that is not in this conventional structure but stored right here at the midpoint of the edges or at the midpoint of the faces.
Are the meshes always before connection, or do you also have hexagonal?
Hexagonal. Yes, we have hexagonal. Yes, we have them. They are first-class citizens. Okay, in the VTK data structures, there exist. In fact, yeah, I helped put that into place several years ago. The VTK prism, the VTK, what is it called? Hexagonal prism and pentagon-based prism, which means that the pentagon exists as a cell, the hexagon exists as a cell, etc. There is a case where some people use spectral codes, and this is similar. In spectral codes, the data for rendering purposes is actually triangularized or tetrahedralized, and we see actually additional lines connecting those vertices together. And it would be the same case with the hexagons, that for rendering purposes we would see the additional triangles, but internally they are used as hexagons and etc. I think that's all I need to say for now. Interesting, we didn't see that yesterday. We can also have the case where we have materials. Okay, this is often found in chemistry, for example, where we have volume fractions, area fractions. So this is the case where we have different volumes, different materials which don't occupy the full 100% of a cell. So this can be done perfectly well with VisIt. Example, yeah, in chemistry where a particular material like the air is composed of many gases. So here are the 4 persons who are responsible for the tutorial. So Cyrus, Hank, Brad, and myself. There. Terminology in VisIt, we talk about zones and nodes. Zones are the same thing when I say cells or elements, finite elements, they're the same thing. Well, VisIt calls them zones, so this is to know. And then fields are called, well, scalars and vectors, and so forth. There's nothing new here. Pseudo-coloring will be the first tool we will learn, and pseudo-coloring is just like we used to color geographic information like this with colors. We do the same in 3D. This is scalar to color mapping, but we call this pseudo-color in VisIt. Contouring, going from 2D to 3D, there should be no secret here for you. You know what an isocontour is. Volume rendering is a little bit different. We have not seen it yesterday. I will show you an animation I have made here with VisIt, which uses volume rendering. It will be a lot more interesting than seeing a static image like this. In fact, why don't I show you this video immediately as a motivating instrument. Of course, I have to find it. There we go. This one, or this one, or this one, this one. Echo. So here's another example of a video which was made on ROSA, on the supercomputer. So this is a data simulation from some colleagues at ETH Zurich. We're looking at the flow through this piston going into the combustion chamber here. And this what we see here is this volume rendering. So volume rendering is a display of there's no polygonal surface, no polygonal elements, but we do a simulation of the integration of the light traversing a semi-opaque object. So this video is actually, you see, a time-dependent problem. And to make it all synchronized, there's quite a lot of work. So a lot of Python programming to be able to reuse and to restart the simulation at the right place, etc. There. So I think we've had a very quick look at volume rendering with this particular example. Volume rendering, just to finish, is a very expensive technique to compute. I cannot pretend to make a volume rendering on my screen and then move around with the mouse, and it's not interactive at all. So if you want to do something like this, please talk to me. There's a lot of optimizations that need to be put in place to make it a useful and effective experience. Particle advection, really the foundation of flow visualization. The problem is this, moving a particle through a vector field. And this is what we will do in our exercise. Already this morning somebody was asking me about streamline. It was you, yeah. So we're going to do streamlines this morning with the exercise. Here we have a very crude display of a vector field. I hardly ever do this type of display anymore because it's not very pretty. We have a vector field, so little arrows, but they all bunched up like this, or here we have some empty space. It's not very effective. There is a technique called line integral convolution, and N2O2, argon, CO2, etc. You can have all those different species as percentages of the full cell value. So the abstractions are the following in VisIt: the databases, the plots, the operators, the expressions. Expression, there's a very simple case. Somebody asked me this morning before we started. I read my data. I have velocity data in my file, but VisIt doesn't see the velocity field. Why not? In the particular case, my guess is that VisIt reads the three components of velocity as individual scalars, and that's it. And this is where we use expression, which is a way to derive additional expressions, yeah, so to speak. And this is very, very trivial to say velocity is actually a composition of the u, v, and w parameters. So this is not a problem. Queries, we saw some queries yesterday. Today we're going to see more queries, and we're going to do this in the exercise, so you'll have to follow carefully. Pipelines, this is my favorite topic. So here's how pipelines are organized in VisIt. We're going to see several scenarios. The first one will be to open a database and do a plot. Okay, the plot is the name inside VisIt which you need to do, and the plot is how you render your data, and then you can modify the way you render your data by adding an operator. So the operator will transform your data. For example, plotting a grid of data will show you the bounding box of your data. If you modify it with an isocontour operator, you will see the isocontour. So this will be really if you follow me carefully, it's a little bit different than ParaView, where I build the pipeline from the top to the bottom and I keep adding things. Here, I do a database, here, a plot, and when I put an operator, the operator is inserted in between. And here you can insert multiple operators, but the plot is always at the bottom of the pipeline. Okay? Of course, you can put your expression here before the plot, etc. Here's an example. Calculate the magnitude of the velocity. This would be typed exactly like this, so it's very close to your standard mathematical notation. There's a full, long database, pipeline, I want to say, a database, an expression, an operator, a plot, and a query. When we query data, there will be the option to query the original data, meaning the data at the very top of the pipeline, or to query data at an intermediate step of the pipeline. So we'll have to be careful in the graphical user interface to say plot the actual data or plot the original data. Aha, so this is where I have to work here. Database, plots, operators, expressions, queries. All of those you see at those following addresses on the wiki, and I'm going to start very simple with a demonstration. The advantage of VisIt when you install it on your computer, it installs a small set of data files which are used for the wiki and for the tutorial. So it's all embedded in a single installation package. And they are found in a subdirectory called data. Today we're going to look at VisIt, and we're going to change things a little bit from yesterday because of the nature of VisIt. We will not have to mess up with this complicated tunnel thing and SSH multiple connections, because VisIt has it all embedded into one click. That's one advantage of it. The other thing that will change is that I have prepared one big exercise, and we've tested this already I personally tested this exercise at the Supercomputing Conference tutorial last November in Denver, and it worked out quite well. So I'm hoping we have the same success here. So this is a fluid flow showcase exercise, probably more than 30 minutes. We'll see how much we get along. The data has been prepared for you. It's here at CSCS under the course directory. This is what we'll intend to do. And then the rest should actually be shorter. This is why I feel we can steal some time from the second part of the morning to accomplish what we did. So let's get started anyway to not waste any more time. VisIt is available at CSCS on Eiger, Pilatus, yes, Castor. As of yesterday night on Rowthorn. Rowthorn is a machine at CSCS that may be interesting for you because it has 2 terabytes of RAM. It's the only such machine with a large memory available. VisIt is also available on Rosa and on Daint. Well, Daint is not open to the public yet, but Rosa is available. Some of you must be users of Rosa. I've done actually a full-length movie of fluid dynamics this last summer on Rosa, so I can tell you it works really well. How do you do it? You develop your Python script using the graphics cluster, and when you have a Python script, you run it on the supercomputer. That's really the way you should use it. And it's keep in mind that it's much cheaper to run on the supercomputer than on the Eiger node, because it's also much more efficient. Presumably, you run your simulations on Rosa, so your data are dumped onto the scratch file of Rosa. If you do the visualization on the same machine, there's no data copying anywhere. It's all one-stop shop. If we run VNC at CSCS, we'll have to use this particular option minus hardware-accel on Eiger. But let's try maybe to, oh, actually, those of you who have not installed VisIt yet, you'll have to go through this. So this is the opening page of the tutorial in Denver, which we did. The full-length tutorial, just like yesterday, is found on the wiki at this particular address. So visitusers.org. That's the point of reference where you'll find everything else. And this is a reduced version of the tutorial. of November. So there is basically fundamental concepts which are explained, and I think I can go a little bit faster here because we've learned some of this yesterday. Then there will be a guided tour by myself, and you should follow along what I do. And then this exercise, which is the blood flow inside an artery with an aneurysm. And so we have flow here going up like this, and then into this aneurysm. There's a lot of vertical structures here, and then the flow finally comes out. And we're going to do several exercises with this data set. This is a time-dependent data set. Some of the exercise will be with the first time step, just to get some practice, and then eventually for the more advanced users, you'll be able to do the full particle animation. So if I open my file like this, and I have to find where I put it, which is something interesting. This is a challenge. Oh, there we go. So app data, VisIt 201, data. There we go. All the examples that are provided with the installation of VisIt are in the silo data format. And the first one we usually use for tutorials is called noise.silo. So I will open this file. Wonderful. Maybe the path is invalid here. Try to use the following format. This is unexpected. I'm not sure this path is actually correct. Open file. Wait, I have to see. So here's what the reason is I've never read data on my laptop. I always read data on the remote server. So I'm going to go directly to the remote server, and that will take care of it. Launch, advanced, minus reservation equals course. Okay. I have some data loaded. And the first questions beginners ask is, I loaded my data and there's nothing on the screen. That's the first barrier. How do we verify that the data has been loaded? Here there's a menu called File Information, and it shows that I have loaded a data set here, which is stored on the Eiger file system. It's of file format silo. It has one time step. It has one mesh called mesh. It has another mesh, which is a two-dimensional mesh called mesh 2D. it has a point mesh, it has scalar fields. One of them is the air volume fraction, the other one is the chrome volume fraction, etc., etc. So it's there. And by the way, in addition to the variables that are stored in the file, I already have some expressions which are predefined. Here, for example, I have the tensor components. So a tensor, this is the 3x3 matrix of the gradient of the velocity vector. And those are automatically defined for me by the VisIt software. I have a couple of fields